who noticed him and invited him to her group. And during these recent years, his research interests focus on search for origin of life. And today we are going to listen to around about this subject. So I think it is a time to give opportunity to our guest to present his results. If you would like to ask a question, you are welcome to raise hand. There is when you click on the participants icon, there is a small sign raise hand in the right bottom corner of the screen. So please ask a question after raising a hand. Yes. So Janusz, you are welcome. Please.
Thank you very much. I hope that you hear me well. I should get and I try to share my screen, but the sharing capabilities are currently not switched on. So let me just do it.
It should be fine.
Fantastic. Okay. So let's see how it works now. You should see my screen.
We can see
right now, and I hope that.
Yes.
Fantastic. So thank you very much for the invitation. I mean, it's a really, and for a kind introduction also. It gives an overview of my rather convoluted career, if you can call this like that. Yes, I am a biologist. I then switched the fields to biophysics. Then I came back to biochemistry for a short while, and now I proudly call myself astrobiologist, which still probably brings a smile to people's faces. And but I hope I will try to convince you that astrobiology is actually a serious science, and that it's something that it is actually a science that is also developing rather vigorously. And what we are going to talk about today is our work that we do on exoplanets, but also on all kinds of on life itself. And we are going to talk about broadly about astrobiology, that what we do around it, and also essentially how we are searching for life on other planets, and what we actually could in principle also expect there. Because because of course astrobiology, as I mentioned, is a science that is relatively new, or it's at least recognized as a legitimate field of study. Not so long. It was recognized as a legitimate field of study not so long time ago. I remember when I actually tell people that I'm very interested in this field, and it is now many years since I actually started being interested in it. People always treated this a little bit as a sort of with a little bit of a smile. But since recent years, I mean, astrobiology really developed, and it actually even got its own NASA-approved official definition, which means that it's really heading towards a bright future, hopefully. And it's essentially it's defined as an interdisciplinary scientific field that is concerned with the origin, evolution, distribution, and future of life in the universe. And particularly, it asks the question: are we alone in the universe, in the galaxy, and how common extraterrestrial life is, if it exists? And of course, apart from that, how can we also detect it? So this is a rather straightforward definition. Reality is, of course, much more complicated, as it often is with very simple definitions. The reality doesn't really match this very well. In this case, we have a situation that astrobiology is essentially a collection of all kinds of topics and disciplines and studies that contribute together, all of them contribute together to answer towards understanding and answering this rather profound question: Are we alone in the galaxy? Are we alone in the universe? And so essentially, you can see there is a lot of different topics that have to work in concert. A lot of disciplines that have to contribute and work in concert to actually help us do our studies and answer this question. So if we have such a problem, actually, where do we even start our research? Where do we even go from here? And we could, for example, start from finding a planet, because if we actually were to look for life elsewhere, we probably should start on a planet. We probably should start by finding a planet, and preferably a habitable one. Since the first discoveries of exoplanets 25 or so years ago, we now know from all kinds of exoplanet census that planets are very common. So essentially, even if you look at our night sky, we see all kinds of stars, and we can now essentially statistically say that virtually every star on our night sky or in the galaxy has a planetary companion, and that essentially that planets are very common and planetary systems as well. And a very, very famous and fashionable technique that is used for planet detection is called the transit method, and it's actually a rather straightforward method when there is a measurement of a dip in the brightness of the star as the planet actually orbits around it, and then the periodical dips in this brightness are actually an indication of a planet that actually happens to reside in such a system. So this is again this sounds like a straightforward technique, but of course in reality everything is much more complicated, because if we were to focus ourselves on a planet that is habitable, then we have to look for a planet that is about the size of Earth, that receives about the same amount of energy from its star as the sun, as Earth receives from the sun, and has some sort of liquid on the surface, preferably liquid water for life as we know it. So essentially, but we have to realize that Earth is actually many times, 100 times smaller than the sun. It is 300 times less massive and many times fainter than the sun. So it's actually, so to detect a planet like Earth is actually not a trivial task. And therefore we actually look not only for planets that are orbiting sun-like stars, like G-type stars, but we actually focus our search as well on planets that orbit a very different stars, much smaller red dwarfs, or M dwarfs as they are called, when the detection conditions are actually much more favorable. So we actually have higher probability of actually finding such planets. And indeed, from over the years, we can now say that we have a lot of different planets detected. We have in many different planetary systems. Exoplanets are extremely diverse. We have range of sizes, range of masses, range of orbits that are very diverse. We have all kinds of planetary systems architectures. And it is also worth mentioning that transit method is not the only method that is used for planetary detection. There is also, of course, radial velocity and microlensing, and even direct imagining of exoplanets. So we can even try those techniques as well. And all of them have their pros and cons, their positives and their negatives. But none of them actually resulted yet, at least yet, in a discovery of a classical Earth twin, because this is indeed a difficult task still. We have to also realize that in our search for a habitable planet, or indeed a planet that is inhabited by life, the detection of a planet is only a first step. It's not enough information just from a planet detection to figure out if a planet is actually habitable. We have to we have to know much more about the planet itself to actually figure out if it is even a good target for search for life elsewhere. And for example, I mean, if we looked from the point of view of exoplanet research, Venus and Earth would look the same to any planet finding technique, and yet the conditions on those two planets are completely different. So essentially, some further characterization of those planets is absolutely needed. And one of those characterizations is, of course, finding if a planet actually has an atmosphere and what the atmosphere is composed of, what chemistry we can find in the atmosphere. So atmosphere studies are key to if we were to actually find or assess the habitability of a planet. And one of those techniques, one of the techniques that are used to actually figure out what is the composition of the atmosphere, of the chemical composition of the atmospheres of exoplanets is called exoplanet transmission spectroscopy. And in a nutshell, it's based on the fact that the starlight actually gets filtered through the planet's atmosphere, and as it goes through, we can actually collect an absorption line spectrum. And this absorption line spectrum is essentially like a fingerprint of a chemical constituents of the atmosphere of such exoplanets. So we can then analyze this absorption line spectrum and figure out from this fingerprint, essentially from this, what is the chemical composition of a planet, and then figure out, for example, from there, if a planet has potentially maybe habitable conditions from the composition of the atmosphere. But of course, it again sounds rather straightforward, and in reality, of course, it is much more complicated than it sounds. One of the problems is that, of course, only a tiny fraction of a star light goes through the planet's atmosphere, so we can only study very special cases or special planets that have right conditions for exoplanet transmission spectroscopy to be actually a viable technique. But nevertheless, we have some success stories, and the flagship of such success stories is one of those hot Saturn-like exoplanets that are very close to their star, that are actually essentially contain a very large, puffy, expanded atmosphere that is easy to study through the exoplanet transmission spectroscopy technique. And indeed, we can see that we can actually identify some spectral lines, these fingerprints of molecules in this atmosphere in the infrared spectrum. And in this particular case, those authors here were able to detect water feature in the atmosphere of this planet. So this gives us hope that while today we can study only special cases like the very giant planets, maybe in the future, at least in principle, we would be able to do much sophisticated studies. And indeed, yes, today, unfortunately, we can only do this with for giant planets, maybe for planets that are maybe a little bit smaller, like mini Neptunes, but not yet for Earth-like planets. We hopefully are going to be able to do some sort of atmospheric studies in the future when James Webb Telescope is actually will go online. And then hopefully this will allow us to actually study exoplanets that are much smaller. But this depends, of course, when this telescope is actually going to go online. I hope that if I checked last time, it is still scheduled to be launched in 2021, but who knows when it's actually going to happen. So but of course, if we study atmosphere, if we study planetary atmospheres, if we look for various gases in the atmospheres, we are not necessarily only interested in such basic constituents of an atmosphere, like, for example, carbon dioxide or water. While water is actually an important component of life, it is only a first hint that the planet can be habitable. And of course, it also depends on many other characteristics of the planet. What we are really interested in finding are some gases that, in principle, do not belong to such a planet. We hope to find gases that we call biosignature gases. And a biosignature gas is defined as a gas that is actually exclusively produced by life. So it's an exclusive gaseous volatile product of a biosphere, that it's not a product at the same time, that it's not a false, that it doesn't have any false positives, and false positives in this case are defined as gases that are also produced by the planet itself, like for example, by geology or photochemistry. So it has to be only produced by life, and it has to be produced also by life in amounts that are sufficient for us to detect it. The gas has to also be produced in amounts that are sufficient to accumulate in an atmosphere, and these amounts have to be large enough for us to actually detect it remotely with our telescopes. And as of now, unfortunately, there is no such thing as the best biosignature gas, as a bullet, that is a silver or golden bullet, or how do you call this, that will give us an unambiguous sign of life. The most common or most preferred or the favored biosignature gas that currently people are looking at is oxygen, obviously, because it should not be present in our atmosphere, and it's on Earth produced in the process of by the photosynthetic plants and bacteria. So it's a gas that is highly reactive, and it's also constantly removed from the atmosphere, so it has to be replenished. So such gases are actually one of the most favorable as biosignatures. But of course, life on Earth produces all kinds of gases. It produces also methane, nitrous oxide, and other gases that are, for example, in large quantities, that are products of bacterial energy metabolism, for example. And those can be produced in really large amounts, nicely, potentially indetectable, potentially indetectable levels. But we have to be aware that the planet, of course, itself has also the same chemistry to work with, which means that the planet itself can also sometimes produce those gases as well and give us a false impression of a detection of life elsewhere. So we have to be really careful there. Thankfully, life is very complex. Life does all kinds of reactions that we wouldn't expect it to do, and it produces all kinds of complex molecules for sometimes completely unspecified reasons and sometimes in very large quantities. And not only that, it actually makes thousands of them. If we look really at various components of various gaseous products that life actually can make, life on Earth really has a huge capability of producing an unbelievable diversity of various volatile molecules that could be pumped out into the atmosphere and essentially potentially work as a biosignature gas. We have to be aware that it is extremely difficult to predict what biosignature gas is going to be present in an exoplanet atmosphere, because we cannot assume that the biochemistry, that the volatile molecules that life on Earth produces in large quantities are going to be produced also in an exoplanet scenario somewhere completely in a completely different place in the galaxy. We also cannot assume that all these gases that are here produced in only tiny quantities or not produced at all cannot be in principle significant products of volatile products of such an alien biosphere. So in principle, we have to be ready for looking for essentially any atmospheric scenario, because many of the gases that, for example, life on Earth produces them completely because of some evolutionary history events or some even accidents of evolution here on Earth, and yet they are important components of our atmosphere as well. So we therefore try to look at this problem of the complexity of chemistry and the volatile gases that we could in principle look for in various planets holistically. We try to have some sort of holistic approach to this problem of what we could actually find if we don't know what we are looking for. And to this end, we actually create all kinds of algorithms to assess the biosignature potential of essentially every gas, so we can be really prepared to identify biosignature gases of any kind and assess if they could be a product of life or not. And this approach is to a degree validated by the complexity of our own, or chemical complexity of our own atmosphere. If we look at the Earth's atmospheric inventory, we have a situation when at the first glance, we always look, we always think that our atmosphere is actually composed mostly of nitrogen or oxygen, maybe some carbon dioxide and so on. But the reality is much more complicated. We actually have a lot of gases that are pumped out into the atmosphere, and many of them, there are actually dozens of them, and almost all of them are essentially products of life, albeit they are always, or in this case, many of them are produced in only tiny quantities. But this, of course, doesn't have to be exactly like that. It doesn't have to be mirrored by the scenarios on exoplanets. So there might be completely different. So a graduate student in our group, Zhuchang Zhan, is actually tasked he develops this sort of a triage holistic approach to assessment of biosignature gases potential in various different exoplanet scenarios. And this is a relatively simple or a schematic how it is done. We take all kinds of gases that we actually know that exist or can exist, and then essentially look if they have some spectral properties and the spectra available. Then we can create all kinds of exoplanet atmosphere scenarios in various conditions, and we figure out if a certain gas can, in principle, be detected or distinguished from other gases in a given atmospheric scenarios. So if we have, for example, various stellar type of a system, we can have various atmospheric main composition like nitrogen atmosphere, CO2 atmosphere, and so on. And we look if these gases actually are detectable or not. If then we can assess if a given gas is reactive enough or not enough for it to actually accumulate in this atmosphere. If it is actually extremely reactive with various other components of the atmosphere, then unfortunately it might not reside in the atmosphere long enough to actually accumulate in large quantities. It might also be photochemically labeled. It might be completely destroyed by the light itself. And at the end, of course, we also have to figure out that if a gas is there in the atmosphere, then it also can be maybe produced by the planet itself. So we have to address the question of all these false positives that I mentioned, and that could, for example, include the production by photochemistry or geology itself. And then as a bonus, we can look, for example, well, is there a precedent for a production by life on Earth? But this is just an additional perk. So you can ask a question: is there actually is there any gas that stood out from this rather lengthy and theoretical and complicated analysis that we did? And yes, one of those gases was phosphine. Yes, and this is a gas that nobody basically heard before until relatively recently. It is a rather obscure gas that is known only to some industrial chemists and maybe agricultural research stations. But in general, it is a simplest gas that is containing phosphorus. It has the phosphorus atom here in orange that is bound to 3 hydrogen atoms. And it's essentially a gas that is common on certain planets like Jupiter and Saturn, giant planets. But on Earth, its source is actually purely biological. There is no other source of phosphine on Earth apart from biology, well, of course, and human industry as well, which by extension is a biological source. Now, so on Earth, biology produces it, and it's only oxygen-free biology. It's anaerobic biology, but of course, and as an additional fact on it, it's actually on phosphine. It's also extremely toxic for oxygen-dependent life. So it's actually very toxic for us. So we should be very careful when we actually study this in the laboratory as well. So we could ask then, of course, is this phosphine actually a good biosignature? Can we actually detect it if it were present in the exoplanet atmosphere? And this is what also Zhuchang's work actually was all about. And here we can indeed, phosphine has a certain strong distinguishable spectral features. So in principle, you could detect it remotely from in the infrared with future telescopes in principle. But unfortunately, even if it can in principle accumulate in an anoxic atmosphere, it has to, and it doesn't appear to have very common false positive scenarios. It unfortunately requires a huge production rates that are in order for us to actually see it and see it remotely, and it needs a special conditions to be detected. And as a summary, in summary, it looks like if we were to find phosphine on an exoplanet, we would need, as I mentioned, special conditions for it to actually be detectable. And these special conditions can be summarized very simply. You need a low UV environment, because unfortunately phosphine is rather reactive molecule. So it doesn't really stay very long in the atmosphere. It gets destroyed photochemically quite readily. It reacts away. And also it needs, and so the most favorable atmospheric scenario that we have found was an H2 dominated sort of a rocky planet. So it's rather not such a great result. We will think that if phosphine is really present on exoplanets, then we unfortunately are limited to only a very tiny fraction of scenarios, of exoplanet scenarios. And until this day, people still argue if an H2 dominated rocky exoplanets can exist. So we do not even know if such a scenario in principle can happen, but hopefully yes, but we don't know. The point is that if we actually looked for this gas somewhere else, if we looked for it much closer to Earth, and this is something that Professor Jane Greaves did, professor from the University of Cardiff. She decided to look for phosphine in an unusual places in our solar system. It is well known that it is produced that it is actually detected in Jupiter and Saturn, but she actually looked at it on Venus, and this is rather an unexpected target to look for such a gas on Venus. But nevertheless, she embarked on this endeavor to look for phosphine on Venus. And if we think about Venus, it is often called a sister planet to Earth, but it is obviously a great exaggeration. It might be only a sister planet in terms of overall mass or radius or very few physical properties. It definitely is not a sister planet when it comes to the temperature conditions that are on the planet, that are on Venus, or even when it comes to the atmospheric composition, which is actually rather different than what we have on Earth. It's actually mostly carbon dioxide and nitrogen. And there is also this rather peculiar feature of having a complete cloud cover of sulfuric acid, concentrated sulfuric acid clouds, in the atmosphere. So it's definitely not a place that you would call home. It's not a place that you would call habitable. Nevertheless, Jane Greaves from the University of Cardiff, she actually looked at phosphine, looked for phosphine using two facilities. One is JCMT on Hawaii, and the other is ALMA in Chile. And to our amazement, actually, she had a tentative detection of phosphine on Venus through thermal emission. Essentially, we were able to see one single absorption line from phosphine in a millimeter region of the spectrum. And essentially, we saw, at least she saw the single line, but with both facilities at a comparable line depth at the same place. So not only that, we can actually also look at where the phosphine is present in the atmosphere, and this gave us also an interesting result that this signal from phosphine was actually detected in this cloud decks of Venus. Here at the altitude of around 55 kilometers, at around 55 kilometers. Later, modeling by our colleague Hideo Sagawa also showed that the phosphine detection reached that the abundance of phosphine in the atmosphere at this level is around 20 parts per billion. If we actually believe that the detection, if ALMA detection is true, then the distribution of phosphine is not only vertically constrained in a sense that in terms of the fact that it's actually at a certain height in the clouds, but also geographically to a certain degree. We can see that the detection was reported mostly in the mid-latitude region on the planet, while the polar region was actually devoid from phosphine. So, of course, with such an unusual detection and unexpected detection and highly controversial result, you actually would ask if this detection is actually real, and that's an obvious question. For now, we believe yes. It's actually phosphine line, and the reasons are sort of summarized to the following points. Phosphine line was actually seen at the comparable line between two independent facilities, as I mentioned, both GCMT and ALMA. We were able the line measurements are actually consistent under varied and independent processing methods, which was also shown by Jane Greaves and Anita and others. And if we overlap the spectra from two different facilities, we actually can see that there are no other such consistent negative features. You can also ask a question if there are other interpretations of this line, if the signal is actually true. You can ask if this is really a phosphine. We've ruled out, or at least the spectroscopists in our team ruled out any other known reasonable candidate absorptions from other molecules other than phosphine, including SO2, which is one of the closest possible alternative candidates. But of course, since the detection was first announced, there are now archive sort of exploded around this study, and there are multiple different papers that are actually got published. Some people, so the discussion is ongoing. Some people claim that our levels of phosphine are actually lower than we reported. Some people claim that the ALMA observations do not even show the line at all. We do not agree with that. Professor Jane Greaves and Anita Richards are in the process of writing a counter argument. And some other people even looked at other very old data from various probes, like, for example, from Pioneer 13 probes, and we're actually trying to figure out or find out if there are some phosphine signals in the neutral gas mass spectrometry that Pioneer 13 probe did. And they actually claim that there might be actually a tentative discovery of phosphorus ions in this data. So I guess over the next couple of months there will be a back and forth, and people are going to try to figure out if this detection really holds, or if there are some other explanations for it. We shall see. But under the assumption that indeed phosphine is actually present on Venus, which is a very unusual discovery, one has to ask what process is actually responsible for making it. Because in an oxidized planet like Venus, you would not expect this process to actually be efficient, the phosphine production process to be efficient. You have to actually essentially reduce oxidized phosphorus species to phosphine, and it's not something that is actually apparently easy to do on an oxidized planet like Venus. In general, phosphine is present, as I mentioned, on Jupiter and Saturn, and in those cases, its production it's readily available in these conditions because of the three characteristics are met. One is the very high pressure, very high temperature, and a very high abundance of hydrogen in the depths of atmospheres of these planets. And those three conditions, those three conditions are not met on a rocky planet like Venus or Earth, and so the analogous process cannot really happen on a rocky planet. So if indeed phosphine is on Venus, then what process actually can make it? We looked at many different processes. It's also work of of Dr. William Baines from MIT as well. We looked at various chemical reactions that could happen between various constituents of the atmospheres or surface minerals. We looked at various photochemical processes that could, in principle, produce phosphine. We looked at various geological processes and rock chemistry that could, in principle, produce it, or even some other processes like volcanism, exotic sources like lightning, or even meteoritic delivery. We looked at various indirect routes of formation of phosphine, like, for example, we produce some other molecules that could lead, in principle, later on to produce phosphine, like phosphorus acid or various phosphorus oxides reactivity. Nothing appears to readily produce phosphine, at least not in amounts that were initially detected. We actually published this rather lengthy analysis over 100 pages long recently on the archive, and we don't know. Simply, we don't know as of now if phosphine detection is real. We don't know what makes it. That's the answer. It doesn't appear to be made by any known readily available process or any common process. So we are left with a conundrum. And of course, there is a very weird and rather speculative hypothesis that if it is not made, if it's not made abiotically, could it in principle be made by biology? Of course, I do not mean the same biology as on Earth, but some in principle biological process. And this, of course, a highly speculative and hypothetical explanation, but nevertheless, we could entertain the possibility. In principle, it is possible. There could be a biochemical machinery that could do it, but physically, is it possible? We don't know, because we have to be aware of the fact that Venusian clouds are a completely different environment than anything that life inhabits here on Earth. So there is absolutely no parallel between an environment that life lives here on Earth in. Even the most acidic environments here on Earth are nowhere close the acidity that anything alive would have to deal with in the clouds of Venus. Apart from that, of course, there is not so much water there. It's essentially extremely dry environment, which is 50 times drier, if not 100 times drier than the driest plains on Earth. We cannot even transfer our biochemistry to this environment. All kinds of molecules that we are built from are going to be completely chopped into pieces. So we cannot really imagine that to happen. This is exemplified very nicely by addition of sulfuric acid, the concentrated sulfuric acid to sugar, and we just basically completely smashing these molecules to pieces. We just basically creating a lump of carbon, that's it. So it is actually, so if indeed phosphine was detected in this environment, this is a really mystery what process is actually made responsible for making it. And of course we cannot really rule out life as a source of phosphine, but we shouldn't really favor it in any way. We should actually consider first all kinds of other scenarios that could happen. So that's why we should actually study the chemical environment of Venus much more. And hopefully, at least this discovery is going to draw attention to this planet and its chemical environment that's really unique and really interesting. And we hope that we are actually going to do this because we've partnered, Breakthrough Initiatives essentially, is now sponsoring an MIT-led study. It's not a mission yet, it's a concept study of a mission to Venus. And we hopefully, hopefully we are going to shed some light on the chemistry of the clouds of Venus. We are going to look for all kinds of molecules there, and hopefully we will be able to actually get some more information about this planet itself. We are going to have all kinds of different types of missions, the small ones, which is also partnering with the Peter Beck and his company Rocket Lab, and the medium, which hopefully is going to look like a Vega balloon type mission. And I think that this is where I will now going to end. This work is not a one person's job. I am just a glorified spokesperson for many people who actually contributed to it. there are many people who have, of course, shout out goes to Jane Greaves and Anita Richards, who actually were the main observers behind the phosphine discovery. Also to Hideo, whose modeling was instrumental in figuring out how much of the phosphine was actually detected. And of course, to others like Paul and Sukrit, who were the photochemists behind the team, and spectroscopists like Clara Souza Silva, and of course, my boss, Sarah Ziegler, and of course, William Baines, who also looked at all kinds of chemical pathways that phosphine could be produced by. And yeah, thank you very much. That's basically where I am. Thank you.
Yes, this is us who thank you for your amazingly interesting talk. Thank you for introducing to us astrobiology, and I congratulate you on your interesting results. It is time for questions. Are there any questions from the audience?
Yes, if I may, I have one question. Because you mentioned that you started to look, for example, at Venus, at Jupiter, at Saturn to see something else. Have we actually tried to look from space at Earth and to see maybe it will somehow help us to find something new and unusual from the space perspective about Earth and about life on Earth?
Oh, I love this question. I thank you very much for this question. It's actually because there was a program which was called Earth as an Exoplanet, and there are both theoretical works on that, and there was also I think that there was this, I might miss the name of the mission, but there was also I think a epoxy mission or something which actually looked for spectra of Earth from space. And yeah, of course, we can detect oxygen, yes, which is great. Some of those small trace gases, not necessarily. We probably would look. We probably would need. We probably would need better facilities and better telescopes.
Mr. Stolarski has
Yes,
a question.
I have a question. Actually, I would like to congratulate you. This is very nice presentation. And my question is, because probably I don't know if I am the only paleontologist in this group, but maybe. So of course, my perspective is, from the deep time perspective, also looking at the Earth, because the Earth is definitely the planet that the life evolved. So there is, if we look in the deep history of Earth, and we are trying to trace those gases or those molecules that are actually traces of life. So if we go back to the beginning of life, where basically we have anoxic environment, do we have any? What do you think? Were you thinking about this period of life, that life was probably occurring only in the ocean, producing, the question is whether the phosphine, you can imagine that the phosphine was produced during that time, and if this was produced during that time during the history of life on Earth, what would happen to this phosphine especially if it is toxic, to the organisms that start to produce the oxygen? So what type of processes would happen if, because it was a transition from the anoxic to the oxic atmosphere, to the life, and then so how this molecule would fit this big steps in the life on Earth? How you would put this in this context?
Yeah, thank you very much for this question. That's actually one thing which you see. Okay, let me put it this way. I would backtrack a little bit, because this is a very good question. It's a very nice question. We don't know yet how life on Earth exactly produces phosphine. So we don't know exactly what biochemical pathway is responsible for its production. We only know what ecological niches are inhabited by life that produces it, but we don't know how. And the point is that on Earth, those ecological niches, when anoxic life produces phosphine, are almost always rich in phosphorus, organic phosphorus. Because this is another interesting point, that why would life produce a gas on Earth that actually wastes phosphorus? And phosphorus is a limiting nutrient for life on Earth. Yes? Just like nitrogen is to a degree, but phosphorus is even bigger limiting nutrient than phosphorus. So it might very well be that in an Earth-like ecosystem, even anoxic one, phosphine production is never going to be very high, because there has to be a reason for its production, because it's not directly tied to an energy metabolism. It is probably produced for reasons that are completely secondary to every other primary metabolic pathway that life has. So it probably it's tied to the fact that there is always an excess of organic phosphorus around, and that's why life on Earth, the anoxic one at least, could allow itself to actually use this gaseous phosphorus for some other function. That it would normally, it might not do it because of the phosphorus limitation. So that would be my answer. Technically, we could expect phosphine to be produced in much higher amounts on an anoxic Earth back in time, but it would require probably a larger phosphorus abundance than normally, let's say. Okay,
I understand. Actually, we have quite a lot of evidence of phosphorus in early evolution on Earth. There is plenty of phosphorites, but especially during at the transition from the anoxic to the oxic environment, and also from the different ocean hemisphere, from this soda ocean towards the halite ocean. This is the point where we have a very massive occurrence of phosphorus.
So we could talk about this actually, because this is something I would love to talk about this, because we now also we have all kinds of collaborations that also now try to, for example, pinpoint how life on Earth exactly does it. Yes. Mm-hmm. Yeah, absolutely. That would be very interesting discussion. So yes, we can talk about this later offline.
I will drop you a line.
Absolutely. Thank you.
So are there any questions? Other questions?
So I have a quick question, if I can.
Please.
So I wonder if you anyhow just think about the, I don't know, very different ideas for life in the universe. I guess that we have one pattern that works on Earth, and one could imagine that there could be so many other ideas how, I don't know, how biochemistry of life could work, or I don't know, maybe life that evolved on other planets leave different signatures than ours. I don't know.
Thank you for that question, because I was a little bit reluctant in putting too much speculation in my talk. Yes. So I left out much of my speculation about the sulfuric acid biochemistry, which is the craziest idea under the sun, at least under the G-type star. Yes. So answering your question now, the problem is that in principle, water is the only solvent that we know works for life. Yes. But there were various theoretical studies that looked, for example, the work of Ballesteros, that looked at various different solvents, and the so-called exoplanet seas that could happen. And it looks like the diversity of oceans and seas and the composition of it is actually very broad. There might be all kinds of cryosolvents that are going to happen. There might be water, and there might be even solvents like sulfuric acid, maybe less likely because the sulfuric acid is relatively reactive. It might react with rocks. But going back to your question, there are two questions. Is there a possibility, is biochemistry, is any biochemistry capable of actually working in other solvent like sulfuric acid? Let's say sulfuric acid. The answer to that question is yes. We are going to have a very cool paper, a theoretical one, about sulfuric acid biochemistry and how it is in principle theoretically possible. What is actually very improbable, or if not impossible, is the origin of life in sulfuric acid. Yes. So unfortunately, origin of life might not be possible because sulfuric acid is rather aggressive, acidic molecule that might chop into pieces all kinds of molecules before they actually try to build something that is stable in it. So now the question is there even a possibility for life, and this is philosophical for now, is there a possibility for life to adapt while the planet changes its solvent from water to other, like sulfuric acid, for example? What happens to Venus? Because if modeling by Michael Way is correct, then Venus lost its oceans, surface oceans of water, as late as 700 million years ago, and then became this sulfuric acid hellhole that it is now. So is there even a pathway, an evolutionary pathway, in which a biochemistry could adapt to a different solvent? And it's a question without answer, because it cannot originate, most likely it cannot originate again in this environment. It cannot, the water biochemistry cannot function in sulfuric acid. And in principle, you could build some other biochemistry, but how do you get there? It's an open question. And I'm going to have a paper with William Baines on this topic, hopefully relatively soon. So I will maybe notify you when it comes out.
Awesome.
And
awesome.
cryosolvents, it's a no-go because the solubility is too low, and the reactivity you can always tweak, but the solubility is too low. So I would argue that there is no life in the methane seas on Titan.
And how about the most hostile environments on Earth? Are they anyhow close to like these exotic places that you could see in the universe, or?
No, that's the problem. So you see, I will give you an example. The most acidic place on Earth, which is like some acid drainage from Iron Mountains or a Dalol pools in Ethiopia, it's like 5% sulfuric acid, yes? So it's still a solution of acid in water, which is great because life needs water, our life needs water. So it's still a solution of acid in water. But sulfuric acid, so the liquid droplets in the clouds of Venus, for example, are 95% sulfuric acid. It's a solution of water in acid, or 85 or 70% of acid in water. It's a solution of water in acid. It's such an acidic environment that the pH scale doesn't make sense. And you have to have a different Hammett acidity scale to even measure this acidity. It's as acidic as -12. So we don't have even an environment that would be the same, that would be comparable to the Venusian environment here on Earth. That's why if there is very, very hypothetically any life in the clouds of Venus, then it has to be life as we don't know it, even if it is water-based, even if it somehow migrated from the oceans in the past to the acidic clouds today. It still has to be life as we don't know it, because it has to have protection mechanisms from sulfuric acid. And if it adapted somehow its biochemistry to this sulfuric acid that it uses it actively, then we even have no chance of actually predicting it in any reasonable way. That's my answer. Rather lengthy, and I apologize for that, but I hope we can always talk
really
about this offline as well.
Really awesome.
Yes, thank you. Are there any questions?
Sorry, may I still continue a little bit the topic of water and sulfuric acid on
Yes, please.
On Venus. So I was wondering, so probably water used to be there before the sulfuric acid formed, so early in the universe. So basically, how it is now. So when sulfuric there should be at some point sulfuric acid rains, which would react with rock, and the water should form at some point, and where it goes, and maybe it just does not evaporate at the temperatures as sulfuric acid does. It sort of flows into some underground cavities, and this might be a sort of an asylum for anaerobic life on Venus, which is sort of would not require hot temperatures, and is sort of UV is not an issue there. But anyway, if it's not photosynthesis, so they don't need any photons to live there, and maybe somehow they release it from underground. Do people consider this as a possibility?
Not today, not on modern Venus, because modern Venus, the sulfuric acid rain evaporates 40 kilometers above the surface. It's this phenomenon that is called virga. Yes, that the rain, when it falls, it actually evaporates. It's so hot that it evaporates essentially. It gets decomposed before it actually reaches the surface. The surface of Venus is 465 Celsius degrees. So it's actually, so there is no organic chemistry on the surface of Venus. It's so hot. Unless you actually build some life from Teflon, it is impossible, yes? Because essentially it's too hot for any complex chemistry. However, you touched on a very interesting topic and a very interesting point. You see, planets always change. So we see a snapshot of a planet as it is now, but of course, it was not always like that. If modeling by Michael Way is correct, then you had a water-like planet. Venus was an actually quite relatively habitable place from our perspective, even as late as 700 million years ago. There should be, and I don't know how, and I don't know how it looked like, but there should be some evolutionary trajectory of this planet which actually went through the water loss and slow acidification. Now, is this acidification a slow enough process that evolution with this high evolutionary pressure of acidification, that it was enough time for something to actually migrate to the clouds, reside there all the time for the entirety of its life cycle, and then adapt to the even harsher acidic conditions with actually maybe actively producing water in the process? Who knows? I don't know, but there should be. But if there was a gradual change in this planet environment, then maybe life had a chance. We have to remember that our life also resides in our atmosphere, in the clouds, but it always has an intimate relationship with the surface. Yeah. Our life also produces all kinds of weird chemicals, for example, that manipulate the droplets, that try to grab all kinds of nutrients from the droplet as it resides briefly in those cloud droplets, for example, before it gets deposited again on the surface of the planet, that it's habitable. The Venusian life, if it hypothetically exists, it would have to reside in this layer perpetually. This is a challenge in itself. So who knows? But it's a very interesting question, how Venus actually evolved from this water-like planet to an actual acidic place as it is now, and was it a gradual process?
Thanks a lot.
Yeah.
Yes. So maybe I would have a question. Some months ago, there was a work published in Science by a Polish group entitled, I put it on the chat, Synthetic Connectivity, Emergence and Self-Regeneration in the Network of Prebiotic Chemistry. And in this work, the authors show the path from very simple molecules to, by self-organization, to proteins. And does it refer to your work in any way? Is it helpful, the discovery?
Absolutely. Thank you for that question, because this is actually something that I really like. This is a phenomenal story. I mean, it's a phenomenal work. It's essentially top-notch chemoinformatics work, I would say. Why it is so important? Because it actually, you see, the origin of life is what? Oh, I guess in 2 years we are going to have 100 years since the Oparins coacervats, since the first works on origin of life. And I would argue that we don't really have a breakthrough. Yes, we still don't know how life originated on Earth. And what we do in the field of experimental origin of life is we study isolated reactions. For example, let's see, how an adenine, which is the A letter in the DNA, how adenine formed. And then we do that in the lab. And sometimes these conditions are isolated in very special cases, which are unlikely to be present on a prebiotic Earth. So we study all of these conditions in isolation. Of course, I do not want to generalize. Some people try to do this so-called one-pot synthesis, which is actually much more complicated. But in general, what this work does, it is it organizes all of those reactions and tries to find out if there are some other alternative routes to those prebiotic molecules from which life arose, or even identifies some routes that were missing. So for example, people in isolation studied maybe some routes to surfactants like fatty acids, for example. And this works identified that there are some networks or chemical synthetic routes that could happen in principle that connected these other prebiotic molecules to fatty acids. How does it, why this work is also important maybe for the future is that there is a rather philosophical question right now, which I like to think about. Does life really have a choice? And what I mean by that is that if we had a watery planet like Earth and we went back in time to the very beginning of life and we roll everything again, would we get exactly the same DNA, RNA, the same proteins and all of this chemistry that we have in water, mind you, yes? So it's still chemistry in the solvent of water, but do we have only one path towards life formation? And so if we go to other planets somewhere, should we expect DNA, for example? Or should we expect proteins? Should we expect amino acids? Or can we actually have something completely different? You know, what you need is you need to build a polymer of some sort. If you can look at it very, very philosophically again, that almost every reaction that life actually does in terms of building its biomass and all, it's polymerization of stuff. So can you build some other things? This work organizes all of that and asks, can you have maybe some other paths? And maybe if they are able to in the future show that no, in water, you have only one path and it can only lead to this basis, to these amino acids and to these proteins. And then you have also a solution that in water, maybe everybody in the cosmos is the same to a degree, at least at the very basic level, because then evolution takes its path and everybody is super different. But at the very, very core of a biochemistry, maybe everybody is the same in water. And also another thing, and I actually did this, I discussed this paper very briefly with my colleague William, and we ran their software on the very acidic scenario, yes? As I said, that origin of life is very unlikely in sulfuric acid. This was sort of my speculation, yes? Because we didn't, I mean, this is just my observations from the literature and from my own sort of knowledge. But their algorithms, when run in very highly acidic conditions, they actually resulted in only few molecules. Yes? So this shows, this sort of, and I'm actually going to cite them and I'm going to put them, William is going to put this analysis in our paper, because this also can be applied to a degree to the question, is there a possibility of origin of life in some other solvents? Like for example, especially the reactive ones, like sulfuric acid. And the answer might be actually no.
Okay, thank you for this answer. I think it is the time to finish. I hope so Janusz Pętkowski can stay with us for a while if there are other questions, so you can talk after the colloquium. So let me recall that our guest was Dr. Janusz Pętkowski from Massachusetts Institute of Technology. Thank you one more time for accepting our invitation. Thank you for your brilliant talk, and we wish you good luck in your further research. And we are finishing, but please stay online, and maybe there might be other questions.
And I hope that you that you liked what I do, and I hope that you find the presentation actually interesting. I really hope so. Thank you.
We like it very much. Thank you.
Well,
and thank you all for coming, and you are welcome for the next colloquium that will take place in a month and will be devoted to Nobel Prize in Physics of this year.
If I may add a comment, this seminarium has been recorded, and the recording, well, thanks to kind agreement of the lecturer, the recording will be linked to our Conversatorium Colloquium web page. So please look it up there. both recording and slides of this lecture. Thank you.
Thank you.